Good afternoon. Myself, Selva Prakash, working as a assistant professor in Thermodynamics Engineering College. Now we are going to talk about the first law of thermodynamics. You will recall the chapters. The energy cannot be destroyed nor created. Therefore, the total energy of the universe is constant. Energy can, however, can be converted from one form to another form, transferred from a surroundings to the reverse. Now, the spontaneous process of the thermodynamics is the major one. We can understand this by using the evaluated compressor pipes between these joints without outside the interventions. Now the gas in the vessel B will be spontaneously effused into the vessel A, but the one gas is both vessels, it will not spontaneous process that are spontaneous in this directions, not spontaneous in reverse direction. So it can be easily understood by the pictures. Now the spontaneous process is easily observed by the process that spontaneous is the one temperature to another temperature. Above 0 degrees Celsius, it is spontaneous for ice to melt. Below 0 degrees Celsius, the reverse process is spontaneous. Reverse process. In a reverse process, the system changes in such a way that end and surroundings can be put back in their original states by exacting reverse process. Changes in the infinity small is reversible process. Actually, this is the diagram. In this diagram, surroundings and systems heat and the temperatures can be easily explained in this process. Irreversible process consider the piston and movable partition. Vacuum gas can be easily understandable by using this picture in the animations. Irreversible process can be undone by the exactly reversible the same change to the systems. All spontaneous processes are reversible. All real processes are irreversible. Now we can easily understand the entropy process. So in the entropy term is invented by the in the year of 19th century by the Rodel Calcius. The Calcius was convinced of the significance of the delivery at the temperature which is delivered at the Q divided by T. Now entropy can be thought as the measuring the random by using the can be easily thought of a measuring the randomness of a system. So it is related to the various modes of motion in molecules like total energy E and entropy H is a state function. Therefore, delta S equal to S final minus S initial. Q reverse. Q reverse the heat is transferred when the constant is carried reversibly at a constant temperature Q in Kelvin. Increasing of the spontaneous process reversible ideal can understand by easily by the delta S, which means the entropy of the universe is equal to entropy of the system plus surroundings entropy is equal to 0. In reversible conditions, entropy of the universe is equal to the change in entropy system by adding the change in entropy in surroundings is equal to 0. For another simply irreversible cases, that means reverse, real and spontaneous. That means the delta change in entropy universe is equal to change in entropy in system plus change in entropy in surroundings. This is the simply the second law of thermodynamics tells us the entropy of universe does not change for the irreversible process and increases for the spontaneous process. Now the second law of thermodynamics you can't break even the in reversible process. Listen carefully. In reversible process for ideal processes, which means I, irreversible ideal processes, the entropy calculation may be depends upon the delta S means difference in entropy at the universe is equal to difference in entropy in system by adding the difference in entropy in surroundings is equal to zero. Irreversible, real and spontaneous. Delta S universe is equal to delta S system plus delta S surroundings less than zero. Now we can understand the second law of thermodynamics by using the entropy, which means this is the diagram. The variance and the rotations of the molecules, it can be easily derived by the Boltzmann describes the concept of entropy on the molecular level. Now, the temperature is a measure of average kinetic energy of the molecules in a sample, which means, listen carefully in the diagram. Even the first diagram has the same directions in the opposite directions of the another that red color bubble. Now, the second diagram is it's become so the same in the second diagram. The bubbles coming the rotations. The it is the simplest way of understanding of the how the entropy changes due to the molecular scale, which means molecular size. Molecules several types of motions. One is a translation, one is a vibrational, and the last one is the rotational, which means the translational is a movement of entire molecule from one place to another place. Vibrational, periodic motion of the atom within a molecule. Radiational, rotational of the molecules on a axis and rotation about the bonds. Okay, now the terms which can be easily explained by the Boltzmann, the motions of the sample molecules at the particular instant, which can be easily snapshot for the all molecules. Okay, now he refers to this sampling as a microstate of the thermodynamic system. Now the each thermodynamic state has a specific number of microstates, which is denoted as the V is associated with the entropy. We all know about the entropy. Entropy is the in previous explanation, entropy is the change in energy with the respect to rotations and the vibrations. Okay. The mathematical sides of entropy can be easily explained by the S equal to K dot land W. We already know about the W is the microstate of specific numbers and the K is the Boltzmann constant. That value is 1.38 into 10 to the power minus 23 joules per Kelvin. Now, entropy of the molecule scale. Implementation and more particles, more states means more entropy. Okay, higher T means T is a here the T indicates the temperature. Higher temperature means more energy states. More energy states also produce the more entropy. In less structures, gas versus solid, more states equal to more entropy. Now we all know about the number of microstates and therefore the entropy trends includes the increase in the temperature, volume of energy, and temperature, and the number of independent moving molecules in the system. Entropy of the molecule scale implementation, the more practice, more states, more entropy. Higher temperature also indicates that in this one. Okay, now then these are the various methods of rotations. The variance now this is the entropy term. So you can easily understand this now. How the entropy and physical states related. The entropy increases with the freedom of emotions of molecules. The freedom of emotions of molecules means the yes, entropy of the gas less than the entropy of the liquid, less than the entropy of the solid. This is the G represents the gas, L represents the liquid, sorry, and the S represents the solid. Okay, now the oxygen hydrogen bond is very relatable in this problem. So we can how we can easily solve this problem. This is the solution. The solution of a solid have some more entropy and more states, but some water molecules have less entropy. They are grouped around icons. Usually there is an overall increases in exponentially the very changes in the entropy changes. In general, entropy increases when the gases are formed from the liquids and the solids, and the liquids or solubles are formed from the solids, and the number of gas molecules increases and the number of moles increases. These four conditions are similarly relatable with the other ones, so the entropy increases with all these conditions. If the term of thermodynamics, we all know about the third law of thermodynamics, the entropy of the group crystalline substance of zero temperature is zero. So the entropy is equal to K dot 1. W represents the microstatic systems. Here the microstatic systems is equal to 1. So it's become the 0. Means the entropy is 0. Look at the diagram. So we can easily understand the entropy and the temperature graph. In this graph, look at the first phase, which means the solid phase, that is in the purple color. So yeah, I think it's right. So purple color. Then when the solid, it means the gradually growth in between the 0 to something slighter value. And then look at the phase 2. It's when it's becoming melting. After the solid beginning melting, so it turns into the liquid. So at the time, the phase 2 represents the violet color, means a violet color. So it's after the liquid formation, the liquid contains the liquid contaminates into the according to the boiling points. So the gases are formed. I think it's a dark green or color. Entropy, the curve between this temperature and entropy curves represents how the entropy changes according to the physical states. Now we can see the standard entropies. They are molecular entropy values of the substance in their standards. The standard molecular entropy selected for the substance at 298 degree Kelvin gases H2, N2, O2, H2O, NH3, CH3, OH, C6H8. These are the gases. So the entropy value is H2. So it becomes 13.6 and N2 91.5. Oxygen becomes 205.0 and H2 also water 88.8. It's 188.8. NH3 ammonia that becomes 192.5. Ethanol 237.6. Methanol 269.2. Liquids in H2O also it's becoming the gas also. Now it's the second phase of this 69.9 and in the liquid ethanol also becomes a 126.8 and the liquid methanol also contains the 172.8 solids Li, Me, K, C, iron, iron and chloride, perchlorate. Ionizing sodium chloride salts becomes the values like 29.1, 51.4, 64.7, and 27.23, 142.3, 72.2. These are the standard size values. The standard entropies end in to increase in the molar mass. Okay. And the standard entropies also refers the larger molecular and the larger, more complex as the entire entropies, which means the methane, ethane, propane has the different values. So methane CH4 it contains the entropy value at 186.3 joule moles per current. Ethanol. So it becomes the standard entropy value equal to 29.6 joules per mole per current. Now the propane. Propane becomes the standard entropy value is the 270.3 moles per current.